Let's start this exercise then next. Here for the first few exercises we have to express each complex number in the form a plus bi. And the first one is this, the product of 5i and minus 3 over 5 times I. It will become progressively more complicated. The first one of course is quite easy. So we ideally have to start the solution by writing we have. But say I am not going to write those things. Okay, I straight away simply just write the number and do the calculation. So you can already see that 5 and this 5 they cancel each other and you have minus 3, and along with that I square. So I square is what? Minus 1. So that way you get 3. But do not simply write 3. You have to express in this form. So you write 3 plus 0i. In the book it may be given as IB, but whether you write IB or BI it does not matter because complex multiplication is commutative. That's why. Okay, so this is the number. Let's see the next one. The next one involves powers of I to the power 9 plus I to the power 19. So you recall that thing, how we reduce the power by expressing the exponent as 4 times something plus something. Okay. Here for example you can write I to the power 4 square times I, because 4 times 2 is 8 and 8 plus 1 is 9. Similarly here you can write this, because 4 times 4 is 16, 16 plus 3 is 19. So these parts containing I to the power 4 they simply vanish because that I to the power 4 is equal to 1. And you have I plus I cube. Now you already know that I cube is minus I, so that way you get 0, and 0 is 0 plus 0i. Okay, so that is the second one. Number 3, I to the power minus 39. What is the largest, I should not perhaps say largest, but what is that multiple of 4 which goes the closest to 39? 40, because 4 times 10 is 40. So you can write I to the power minus 39 like this, minus 10. So this is I to the power minus 40. Plus 1, minus 40 plus 1 is minus 39, so times I. So this is just I, and so expressed in that form this becomes 0 plus 1i. Next, number 4. Number 4 is 3 times 7 plus 7i plus I times 7 plus 7i. When you look at an expression and you see the same term, same expression, same number 7 plus 7i, there is the temptation to take this common out and write 3 plus I. That won't give us anything because we want to ultimately do the calculation. So that will take us backwards. Three times 7 plus 7i plus I times 7 plus 7i. So this is 21 plus 21i plus 7i plus 7i square. So I square is minus 1. So 21 minus 7 plus, what about this, 28i. That means this becomes 14 plus 28i. Okay, so that's the answer. Yeah. Next, fifth one, 1 minus I minus minus 1 plus 6i you can proceed in slightly different ways for this one. Two slightly different ways. You can straight away apply the definition of subtraction of one complex number from another. Or you can first do this calculation here, multiply this complex number by minus. Okay, so I think the second way is better because there is less chance of making mistake. One minus I minus 1 plus 6i, yeah, that's the number. So this will be 1 minus I plus 1 minus 6i. So that gives us 2 minus 7i. Okay, so that's our answer. Next, 6. 1 over 5 plus 2 over 5i. So that is one number minus 4 plus 5 over 2i. That's the other number. Here, however, you do not have minuses, only you have minus here. So you can straight away apply the definition of subtraction, which tells you to subtract 4 from 1 over 5 and then separately subtract 5 over 2 from 2 over 5, keeping the form intact, that is something plus I times something. That means this is what we do, minus 4 plus minus 5 over 2i. So what shall we get here? 4 times 5 is 20, 1 minus 20 is minus 19. So minus 19 over 5. And what about this 4 minus 25? That means minus 21 divided by 10 I. But let me check also because I keep making mistakes. Minus 19 over 5 minus 20, yes, this is the answer. 7. For the seventh one, okay, so this is a little longer. 1 over 3 plus 7 over 3i plus 4 plus 1 over 3i. But there is more. From this you subtract minus 4 over 3 plus I. You can actually do it at once, although you see a bracket here, I mean a set of brackets. Seven over 3I plus 4 plus 1 over 3I minus 4 over 3 plus I. So if you want to do at once, 1 divided by 3 plus 4 minus 4 over 3 means plus 4 over 3. So that will be the real part. So you just do the calculation of the real parts separately and imaginary parts separately. As long as there is no multiplication of complex numbers, you can just do the real part and imaginary part separately, that's all. Plus, what about the imaginary part? 7 divided by 3 plus 1 divided by 3, the things we have with I, minus I. Okay, you have to be careful with the signs. That means minus 1 I. Now what will you get if you do the calculation? There is no point going through the details of the calculation. I am just simply going to give you the final answer. So the final answer will be 17 divided by 3 plus 5 over 3I, which many of you can almost instantly see because you can calculate much faster than me. Okay, so this is how it's going to be. In fact, if you see 12 plus 4, 16, 16 plus 1, 17, so like that you can verify. Next, 8. Okay, so this one is interesting. The fourth power of 1 minus I. If you want, you can use the, I cannot tell you right now itself about the binomial theorem, no, because we haven't really seen that yet. So let's expand this usual way. I mean, first do a square and then square of that. Actually, that way it's easier. You will see why. So this is what it is, right? But we know the square formula, a minus b whole square. 1 square minus 2 times 1 times I plus I square. So 1 minus 2I, I square is minus 1. So there you see that there is a simplification, 1 and minus 1 cancel each other and you get minus 2I square, which is just 4I square, and 4I square means minus 4, so this is minus 4 plus 0I. Okay, so what at first looked like a very big calculation, it gradually got reduced and you have the answer. Yes. Next. 1 over 3 plus 3I cube. Here you have to use a plus b whole cube formula. Same formula that you have used always for real numbers is also available for complex numbers. There is no change in the form of the formula. a cube plus 3 times a square times b plus 3 times a times b square plus b cube. Okay, now you have to carefully do the calculation. 1 divided by 27. You see, here the denominator will be 9 because there is a square, and the numerator is also 3 times 3, 9. That means this term is I. What about this? 3 and 3 already they cancel each other. 3 square is 9, but we have I square with that, and I square is minus 1. So that means minus 9. What will happen to this? 3 cube is 27, but with that you have I cube, and I cube is minus I. So minus 27I. Okay. So that way you are, if you do the calculation, finally you are going to get this minus 242 divided by 27. The real part you have to do a little calculation, but the imaginary part is minus 26. So this is minus 26I. And there is another one like this, 10. This one is minus 2 minus 1 over 3I cube. To simplify it slightly, what you can do is that you can first of all take the minus outside, because there is cube, so it will be there, minus won't vanish. And after doing that, you have this 2 plus 1 over 3I cube. So now you apply your formula. 2 cube plus 3 times 2 square times 1 over 3I plus 3 times 2 times I divided by 3 square plus this cube. Don't forget the outermost set of brackets, because there is a minus. So that means minus 8. And then what? 3 and 3 get cancelled. 2 square is 4. So plus 4I. What happens here? You have 2 divided by 3. But because of I square, you see, you have 3 square, right? And 1 3 and 1 3 get cancelled. So 2 divided by 3 with I square, that means minus 2 divided by 3. And just like that previous calculation, this becomes minus 1 divided by 27I, because I cube is minus I. And here, if you do your calculation, you will finally get what? Minus 22 divided by 3. Oh, see, I myself messed things up. See, this is what happens when we are careless. That's what I was thinking, why it's not coming. See what I did? I forgot the outermost set of brackets. That's why I was going to calculate minus 8 minus 2 over 3. So that won't be this. But now it's okay, because 24 minus 2 is in fact 22. And with that, we also have minus 107 divided by 27I. So this should be the answer. Okay, so in these exercises we had to express the given number in the a plus bi form. Next, find the multiplicative inverse. inverses of this next 3 exercises. The next one, that means the 11th one, has this number 3 minus 4i, sorry 4 minus 3i. Okay, so we are going to do it this way. We are going to use the formula for multiplicative inverses, which has complex conjugate and absolute value. That means recall that the multiplicative inverse of z, if z is a non-zero complex number, is this. This is what we are going to use here. And you have to write like this: let z be the given complex number, then its complex conjugate is obtained by changing the sign of the imaginary part, 4 plus 3i. And what about the square of its modulus? Do not forget that if you simply write modulus, there is a square root, but because you are taking squares, so the square root won't be there. Sum of the squares of the real and imaginary parts, 4 square plus minus 3 square, that means 16 plus 9, 25. So that means 4 plus 3i divided by 25, or in other words 4 over 25 plus 3 over 25 times I. You can actually do this in one other way also. So let me give you an alternative. Just for this one, let me show you an alternative way. You straight away write the multiplicative inverse of 4 minus 3i is, and then you write this. What you do, you multiply and divide by the complex conjugate of the given number. And then you do the calculation, you will get the same thing. It's up to you which one you want to use. Next, 12. Here the number is square root of 5 plus 3i. Let me do it this way. Okay. So the multiplicative inverse will be equal to minus 3i root 5 minus 3i. Okay, so what are we going to get here? A plus b times a minus b, so a square minus b square minus b square. Do not forget minus b square. And what is our b? 3i. Numerator of course will stay as such. Now what shall we get? Root 5 square is 5. 3 square is 9. I square will be minus 1. Already there is a minus. So that means 5 plus 9 means 14. So this will be root 5 minus 3i divided by 14. minus 3 divided by 14 times I. It's a good habit of writing the final answer in this form. Okay, even if it is not explicitly said that you have to write a complex number like this, it's a good habit to write like this. It clearly shows what the real part and imaginary part are. I think there is one more here. 13. This is minus I. Now the simplicity of this number should not throw you off. Okay. You follow the exact procedure and do whatever is needed to be done in this case also. Suddenly, because it looks like a very simple number, you don't get confused. Because it is also a complex number. So again, let me go back to the original method. Then, what is the complex conjugate? That will be obtained by changing the sign of the imaginary part. The imaginary part here is minus 1. So that means now it will be plus 1. And so the number will be I. And if you write this number in the form a plus ib, it looks like this. So that's why absolute value of z square will be this. That is 1. So if you really are using this formula, first you write the formula. Okay, do not straight away write the numbers. It shows that, I mean, I'm talking about examination, of course. It shows, if you write this, then the examiner knows that you know. Otherwise, it will look like you have copied from someone else. That should not happen. So, z bar is I and divided by 1. That means I. So, you must see a peculiar thing here. The additive inverse of I by definition is minus I, just like the additive inverse of 1 is minus 1. But the multiplicative inverse of I is also minus I. Actually, the multiplicative inverse, what we have shown here is that the multiplicative inverse of minus I is I, but the same can be said about these numbers when you switch the order. Okay. And finally, there is one more in these exercises, the 14th one. This is the last one. This final one is also expressed in the form a plus bi, and the number is this: 3 plus root 5i times 3 minus root 5i divided by root 3 plus root 2i minus root 3 minus root 2i. The authors have deliberately chosen, intentionally chosen this form to confuse the student. If you have the habit of hurrying things, if you are in a haste, if you do matters hastily and carelessly, you may forget that here we have a minus. It's not product like the numerator. Instead of again writing this number, let me write what it will become. if you do the multiplication using a plus b times a minus b formula, you get 3 square minus this, and now in the denominator root 3 and minus root 3 cancel each other, and you have root 2i minus of minus root 2i means plus root 2i, so 2 root 2i. So you can see that instantly what at first looks like a very complicated expression has been simplified. So this will be what? 9. I square is minus 1, minus and minus give us plus root 5 square is 5 to root 2i. 14 divided by 2 root 2i. Now what will you do about this I? Just now we saw that the numbers I and minus I are inverses of each other, multiplicative inverses. So you multiply and divide by minus I. What will that do? Well, if you want, you can cancel 1, 2 here. I am going to do it afterwards. Minus I square. I square is minus 1, so this is plus 1. That means this is what we will have. So 0 minus 7 divided by root 2i. If you don't like square root in the denominator, you can multiply and divide by root 2 and express the number like this. Minus. Okay, so that's it. These are the exercises. Okay, so let me just end the video here itself, and tomorrow also, of course, we have our upload and we will see what it is. So see you tomorrow with a new upload. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.